Calcium carbonate is a chemical compound with the formula CaCO3. It is a common substance found in rocks in all parts of the world, and is the main component of shells of marine organisms, snails, cold balls, pearls, and eggshells. Calcium carbonate is the active ingredient in agricultural lime, and is created when Ca ions in hard water react with carbonate ions creating limescale. It is commonly used medicinally as a calcium supplement or as an antacid, but excessive consumption can be hazardous. Chemistry. Calcium carbonate shares the typical properties of other carbonates. Notably, it reacts with strong acids, releasing carbon dioxide, CaCO3, S, plus 2HCl, AC, a CaCl2, AC, plus CO2, G, plus H2O, L. It releases carbon dioxide on heating, called a thermal decomposition reaction, or calcination to form calcium oxide, commonly called quicklime, with reaction enthalpy 178 kJ per mole. CaCO3, S, a CaO, S, plus CO2, G. Calcium carbonate will react with water that is saturated with carbon dioxide to form the soluble calcium bicarbonate. CaCO3 plus CO2 plus H2O or Ca, HCO3, 2. This reaction is important in the erosion of carbonate rocks, forming caverns, and leads to hard water in many regions. An unusual form of calcium carbonate is ecate with crystal water. CaCO3 is 6 hours 20. Ecate is stable only below 6 degrees Celsius. Preparation. The vast majority of calcium carbonate used in industry is extracted by mining or quarrying. Pure calcium carbonate can be produced from a pure quarried source. Alternatively, calcium carbonate is prepared from calcium oxide. Water is added to give calcium hydroxide, and carbon dioxide is passed through this solution to precipitate the desired calcium carbonate, referred to in the industry as precipitated calcium carbonate. CaCO3 or CaO plus CO2, CaO plus H2O or Ca, OH, 2, Ca, OH, 2 plus CO2 or CaCO3 plus H2O, occurrence, geological sources, calcite, aragonite and waterite are pure calcium carbonate minerals. Industrially important source rocks which are predominantly calcium carbonate include limestone, chalk, marble and travertine. Biological sources, eggshells, snail shells and most seashells are predominantly calcium carbonate and can be used as industrial sources of that chemical. Oyster shells have enjoyed recent recognition as a source of dietary calcium, but are also a practical industrial source. While not practical as an industrial source, dark green vegetables such as broccoli and kale contain dietarily significant amounts of calcium carbonate. Geology. Carbonate is found frequently in geologic settings and constitute an enormous carbon reservoir. Calcium carbonate occurs as aragonite and calcite. The carbonate minerals form the rock types, limestone, chalk, marble, travertine, tufa, and others. Purity of calcium carbonate has been found in some mines to be 99.2% pure. In tropic settings, the waters are warm and clear. Corals are more abundant in this environment than towards the poles where the waters are cold. Calcium carbonate contributors, including plankton, coralline algae, sponges, brachiopods, echinoderms, bryozoa and mollusks, are typically found in shallow water environments where sunlight and filterable food are more abundant. Cold water carbonates do exist at higher latitudes but have a very slow growth rate. The calcification processes are changed by the ocean acidification. Where the oceanic crust is subducted under a continental plate, sediments will be carried down to warmer zones in the asthenosphere and mesosphere where the calcium carbonate is decomposed to carbon dioxide which will give rise to explosive volcanic eruptions. Carbonate compensation depth. The carbonate compensation depth is the point in the ocean where the rate of precipitation of calcium carbonate is balanced by the rate of dissolution due to the conditions present. Deep in the ocean, the temperature drops and pressure increases. Calcium carbonate is unusual in that its solubility increases with decreasing temperature. Increasing pressure also increases the solubility of calcium carbonate. The CCD can range from 4 euro 6 km below sea level. Taphonomy, calcium carbonate can preserve fossils through permineralization. Most of the vertebrate fossils of the two medicine formation a geologic formation known for its duck-billed dinosaur eggs are preserved by Co3 permineralization. This type of preservation preserves high levels of detail, even down to the microscopic level. However, it also leaves specimens vulnerable to weathering when exposed to the surface. Uses: industrial applications. The main use of calcium carbonate is in the construction industry, either as a building material or limestone aggregate for road building, or as an ingredient of cement, or as the starting material for the preparation of builder's lime by burning in a kiln. However, due to weathering mainly caused by acid rain, calcium carbonate is no longer used for building purposes on its own, and only as a raw primary substance for building materials. Calcium carbonate is also used in the purification of iron from iron ore in a blast furnace. The carbonate is calcined in situ to give calcium oxide, which forms a slag with various impurities present, and separates from the purified iron. In the oil industry, calcium carbonate is added to drilling fluids as a formation bridging and filter cake sealing agent. It is also a weighting material which increases the density of drilling fluids to control the downhole pressure. Calcium carbonate is added to swimming pools, as a pH corrector for maintaining alkalinity and offsetting the acidic properties of the disinfectant agent. It is also used as a raw material in the refining of sugar from sugar beet. It is calcined in a kiln with anthracite to produce calcium oxide and carbon dioxide. This burnt lime is then slaked in sweet water to produce a calcium hydroxide suspension for the precipitation of impurities in raw juice during carbonatation. Calcium carbonate has traditionally been a major component of blackboard chalk. However, modern manufactured chalk is mostly gypsum, hydrated calcium sulfate Car-So-For 2-Hours-Duo. Calcium carbonate is a main source for growing secrete, or rock. Precipitated calcium carbonate, pre-dispersed in slurry form, is a common filler material for latex gloves with the aim of achieving maximum saving in material and production costs. Fine-ground calcium carbonate is an essential ingredient in the microporous film used in babies' diapers and some building films, as the pores are nucleated around the calcium carbonate particles during the manufacture of the film by biaxial stretching. GCC or PCC is used as a filler in paper because they are cheaper than wood fiber. In terms of market volume, GCC are the most important types of fillers currently used. Printing and writing paper can contain 10–20% calcium carbonate. In North America, calcium carbonate has begun to replace kaolin in the production of glossy paper. Europe has been practicing this as alkaline papermaking or acid-free papermaking for some decades. PCC has a very fine and controlled particle size, on the order of 2 micrometers in diameter, useful in coatings for paper. Calcium carbonate is widely used as an extender in paints, in particular matte emulsion paint, where typically 30% by weight of the paint is either chalk or marble. It is also a popular filler in plastics. Some typical examples include around 15 to 20% loading of chalk in unplasticized polyvinyl chloride drain pipe, 5 to 15% loading of stearate-coated chalk or marble in UPVC window profile. PVC cables can use calcium carbonate at loadings of up to 70 pHr to improve mechanical properties and electrical properties. Polypropylene compounds are often filled with calcium carbonate to increase rigidity, a requirement that becomes important at high use temperatures. Here the percentage is often 20–40%. It also routinely used as a filler in thermosetting resins and has also been mixed with ABS, and other ingredients, to form some types of compression molded clay poker chips. Precipitated calcium carbonate, made by dropping calcium oxide into water, is used by itself or with additives as a white paint, known as whitewashing. Calcium carbonate is added to a wide range of trade and do-it-yourself adhesives, sealants, and decorating fillers. Ceramic tile adhesives typically contain 70–80% limestone. Decorating crack fillers contain similar levels of marble or dolomite. It is also mixed with putty in setting stained glass windows, and is a resist to prevent glass from sticking to kiln shelves when firing glazes and paints at high temperature. In ceramics glazing applications, calcium carbonate is known as whiting, and is a common ingredient for many glazes in its white powdered form. When a glaze containing this material is fired in a kiln, the whiting acts as a flux material in the glaze. Ground calcium carbonate is an abrasive, in particular in its calcite form, which has the relatively low hardness level of 3 on the Mohs scale of mineral hardness, and will therefore not scratch glass and most other ceramics, enamel, bronze, iron, and steel, and have a moderate effect on softer metals like aluminium and copper. A paste made from calcium carbonate and deionized water can be used to clean tarnish on silver. Health and dietary applications. Calcium carbonate is widely used medicinally as an inexpensive dietary calcium supplement or gastric antacid. It may be used as a phosphate binder for the treatment of hyperphosphatemia. It is also used in the pharmaceutical industry as an inert filler for tablets and other pharmaceuticals. Calcium carbonate is used in the production of toothpaste and has seen a resurgence as a food preservative and color retainer, when used in or with products such as organic apples or food. Excess calcium from supplements, fortified food and high-calcium diets, can cause the milk alkali syndrome, which is serious toxicity and can be fatal. In 1915, Bertram Sippy introduced the Sippy regimen of hourly ingestion of milk and cream, and the gradual addition of eggs and cooked cereal, for 10 days, combined with alkaline powders, which provided symptomatic relief for peptic ulcer disease. Over the next several decades, the Sippy regimen resulted in renal failure, alkalosis, and hypercalcemia, mostly in men with peptic ulcer disease. These adverse effects were reversed when the regimen stopped, but it was fatal in some patients with protracted vomiting. Milk alkali syndrome declined in men after effective treatments for peptic ulcer disease arose. During the past 15 years, it has been reported in women taking calcium supplements above the recommended range of 1.2 to 1.5 Ag daily, for prevention and treatment of osteoporosis, and is exacerbated by dehydration. Calcium has been added to over-the-counter products, which contributes to inadvertent excessive intake. Excessive calcium intake can lead to hypercalcemia, complications of which include vomiting, abdominal pain and altered mental status. As a food additive it is designated E170. INS number 170. Used as an acidity regulator, anti-caking agent, stabilizer or color, it is approved for usage in the EU, USA and Australia and New Zealand. It is used in some soy milk and almond milk products as a source of dietary calcium. One study suggests that calcium carbonate might be as bioavailable as the calcium in cow's milk. Calcium carbonate is also used as a firming agent in many canned or bottled vegetable products. Environmental applications. In 1989, a researcher, Ken Simmons, introduced CaCO3 into the Whetstone Brook in Massachusetts. His hope was that the calcium carbonate would counter the acid in the stream from acid rain and save the trout that had ceased to spawn. Although his experiment was a success, it did increase the amount of aluminium ions in the area of the brook that was not treated with the limestone. This shows that CaCO3 can be added to neutralize the effects of acid rain in river ecosystems. Currently calcium carbonate is used to neutralize acidic conditions in both soil and water. Since the 1970s, such liming has been practiced on a large scale in Sweden to mitigate acidification, and several thousand lakes and streams are limed repeatedly. Calcium carbonate is also used in flue gas desulfurization applications, eliminating harmful SO2 and NO2 emissions from coal and other fossil fuels burnt in large fossil fuel power stations. Calcination equilibrium. Calcination of limestone using charcoal fires to produce quicklime has been practiced since antiquity by cultures all over the world. The temperature at which limestone yields calcium oxide is usually given as 825 degrees Celsius, but stating an absolute threshold is misleading. Calcium carbonate exists in equilibrium with calcium oxide and carbon dioxide at any temperature. At each temperature there is a partial pressure of carbon dioxide that is in equilibrium with calcium carbonate. At room temperature the equilibrium overwhelmingly favors calcium carbonate, because the equilibrium CO2 pressure is only a tiny fraction of the partial CO2 pressure in air, which is about 0.035 kilopascals. At temperatures above 550 degrees Celsius the equilibrium CO2 pressure begins to exceed the CO2 pressure in air. So above 550 degrees Celsius, calcium carbonate begins to outgo CO2 into air. However, in a charcoal-fired kiln, the concentration of CO2 will be much higher than it is in air. Indeed, if all the oxygen in the kiln is consumed in the fire, then the partial pressure of CO2 in the kiln can be as high as 20 kilopascals. The table shows that this equilibrium pressure is not achieved until the temperature is nearly 800 degrees Celsius. For the outgassing of CO2 from calcium carbonate to happen at an economically useful rate, the equilibrium pressure must significantly exceed the ambient pressure of CO2. And for it to happen rapidly, the equilibrium pressure must exceed total atmospheric pressure of 101 kilopascals, which happens at 898 degrees Celsius. Solubility, with varying CO2 pressure. Calcium carbonate is poorly soluble in pure water. The equilibrium of its solution is given by the equation, where the solubility product for Ca2 plus CO32 is given as anywhere from Ksp equals 3.7 A, 10⁹ to Ksp equals 8.7 A, 10⁹ at 25 degrees Celsius, depending upon the data source. What the equation means is that the product of molar concentration of calcium ions with the molar concentration of dissolved CO32 cannot exceed the value of Ksp. This seemingly simple solubility equation, however, must be taken along with the more complicated equilibrium of carbon dioxide with water. Some of the CO32 combines with H+ in the solution according to HCO3 is known as the bicarbonate ion. Calcium bicarbonate is many times more soluble in water than calcium carbonate. Indeed it exists only in solution. Some of the HCO3 combines with H+ in solution according to. Some of the H2CO3 breaks up into water and dissolved carbon dioxide according to. And dissolved carbon dioxide is in equilibrium with atmospheric carbon dioxide according to. For ambient air, is around 3.5 A, 10⁴ atmospheres. The last equation above fixes the concentration of dissolved CO2 as a function of, independent of the concentration of dissolved Ca2. At atmospheric partial pressure of CO2, dissolved CO2 concentration is 1.2 A, 10⁵ moles per liter. The equation before that fixes the concentration of H2CO3 as a function of CO2. For CO2 equals 1.2 A, 10⁵, it results in H2CO3 equals 2.0 A, 10⁸ moles per liter. When H2CO3 is known, the remaining three equations together with, which is true for all aqueous solutions, and the fact that the solution must be electrically neutral, 2, Ca2++, H+ equals, HCO3 plus 2, CO32 plus, O make it possible to solve simultaneously for the remaining 5 unknown concentrations. The table on the right showed the result for Ca2+ and H+ as a function of ambient partial pressure of CO2. At atmospheric levels of ambient CO2 the table indicates the solution will be slightly alkaline with a maximum Ca2 solubility of 47 mg per liter. As ambient CO2 partial pressure is reduced below atmospheric levels, the solution becomes more and more alkaline. At extremely low, dissolved CO2, bicarbonate ion, and carbonate ion largely evaporate from the solution, leaving a highly alkaline solution of calcium hydroxide, which is more soluble than Ca2. Note that for equals 10 or 12 atmospheres, the Ca2+ OH2 product is still below the solubility product of Ca, OH, 2. For still lower CO2 pressure, Ca, OH, 2 precipitation will occur before Ca2 precipitation. As ambient CO2 partial pressure increases to levels above atmospheric, pH drops, and much of the carbonate ion is converted to bicarbonate ion, which results in higher solubility of Ca2+. The effect of the latter is especially evident in day-to-day life of people who have hard water. Water in aquifers underground can be exposed to levels of CO2 much higher than atmospheric. As such water percolates through calcium carbonate rock, the Ca2 dissolves according to the second trend. When that same water then emerges from the tap, in time it comes into equilibrium with CO2 levels in the air by outgassing its excess CO2. The calcium carbonate becomes less soluble as a result and the excess precipitates is limescale. This same process is responsible for the formation of stalactites and stalagmites in limestone caves. Two hydrated phases of calcium carbonate, monhydrocalcite, Ca2 and Ac8, Ca2 6 hours 20, may precipitate from water at ambient conditions and persist as metastable phases. With varying pH, temperature and salinity, Ca2 scaling in swimming pools. In contrast to the open equilibrium scenario above, many swimming pools are managed by addition of sodium bicarbonate to about 2 mm as a buffer, then control of pH through use of HCl, now HSO4, now 2CO3, now O or chlorine formulations that are acidic or basic. In this situation, dissolved inorganic carbon is far from equilibrium with atmospheric CO2. Progress towards equilibrium through outgassing of CO2 is slowed by the slow reaction H2CO3 AC plus H2O. Limited aeration in a deep water column and periodic replenishment of bicarbonate to maintain buffer capacity. In this situation, the dissociation constants for the much faster reactions H2CO3AH plus HCO3 Euro 3/4 A 2 hours plus CO32 allow the prediction of concentrations of each DIC species in solution, from the added concentration of HCO3, which comprises more than 90% of total DIC from penthouse 7 to penthouse 8 at 25 ESHC in fresh water. Addition of HCO3 will increase CO32 concentration at any pH. Rearranging the equations given above, we can see that Ca2 plus equals KSP slash CO32, and CO32 equals Ca2x, HCO3 slash H plus. Therefore, when HCO3 concentration is known, the maximum concentration of Ca2 plus ions before scaling through Ca2 precipitation can be predicted from the formula, Ca2 plus max equals X. The solubility product for Ca2 and the dissociation constants for the DIC species are all substantially affected by temperature and salinity, with the overall effect that Ca2 plus max increases from fresh to salt water, and decreases with rising temperature, pH, or added bicarbonate level, as illustrated in the accompanying graphs. The trends are illustrative for pool management, but whether scaling occurs also depends on other factors including interactions with Mg2+, B, OH, 4 and other ions in the pool, as well as supersaturation effects. Scaling is commonly observed in electrolytic chlorine generators, where there is a high pH near the cathode surface and scale deposition further increases temperature. This is one reason that some pool operators prefer borate over bicarbonate as the primary pH buffer, and avoid the use of pool chemicals containing calcium. Solubility in a strong or weak acid solution. Solutions of strong, moderately strong or weak acids are commercially available. They are commonly used as descaling agents to remove limescale deposits. The maximum amount of Ca2 that can be dissolved by 1 liter of an acid solution can be calculated using the above equilibrium equations. In the case of a strong monacid with decreasing acid concentration, A equals, or, we obtain, where the initial state is the acid solution with no Ca2+ and the final state is the solution with saturated Ca2+. For strong acid concentrations, all species have a negligible concentration in the final state with respect to Ca2+, and also that the neutrality equation reduces approximately to 2, Ca2+ equals, or yielding. When the concentration decreases, HCO3 becomes non-negligible so that the preceding expression is no longer valid. For vanishing acid concentrations, one can recover the final pH and the solubility of CaCO3 in pure water. In the case of a weak monacid with decreasing total acid concentration, A equals, or plus, AH, we obtain, for the same total acid concentration, the initial pH of the weak acid is less acid than the one of the strong acid. However, the maximum amount of CaCO3 which can be dissolved is approximately the same. This is because in the final state, the pH is larger than the pKa, so that the weak acid is almost completely dissociated, yielding in the end as many H+ ions as the strong acid to dissolve the calcium carbonate. The calculation in the case of phosphoric acid is more complicated since the concentrations of the four dissociation states corresponding to this acid must be calculated together with HCO3A, CO32A, Ca2+, H+, and OA. The system may be reduced to a seventh-degree equation for H+, the numerical solution of which gives, where A equals H3PO4 plus H2PO4A plus HPO42A plus, PO43A is the total acid concentration. Thus phosphoric acid is more efficient than a monacid since at the final almost neutral pH, the second dissociated state concentration, HPO42A is not negligible. See also. References. External links, International Chemical Safety Card 1193, CID 516889 from PubChem, ATC codes, A02 AC01 and A12 AA04, the British Calcium Carbonate Association Euro, What is Calcium Carbonate, CDC, NIOSH Pocket Guide to Chemical Hazards, Calcium Carbonate.